quarter 1, row ID 3, quarter 1. And you'll see there are about 300 rows or values with quarter 1 as the value in the column. So this is what we call a dense B tree. It has one entry for every value in the column. And it turns out you can use a sparse B tree in this case and not store all those row IDs. So you have row ID 1, the value from the column, and then you have row ID 301 and the value Q2. So basically this is saying between 1 and 300, all those column values were Q1, etc. Now, for a long time, people were stuck on these two representations, using a modified B tree or using this DSM model. And finally, Sybase and Vertica, CStore Vertica, came along and said, let's throw all those row IDs away. Let's let the database system keep track of the correspondence between the values in the different columns while it's executing. It can count. So when it reads the first value of the first column and the first value of the second column and the first value of the third column that it's processing, it can count and say, oh, that's the first value. And it can build a sort of in-memory counter that's keeping track, and it will provide the correspondence we need to glue things together later. So the positional representation takes the table on the left and comes back to that sort of picture I alluded to earlier, where I just store the values in the column one after another, dense packed together, no space, not updatable. So here I have my 3 columns, and I'll let the database system compute those row IDs. They're sort of virtual row IDs, and I'll compute them during query processing. Now the beauty of this design is now I have nothing but sorted values. I have Q1, 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 thousands of Q1 corresponding to sales of products. Then a whole bunch of product IDs. You know, because I've done a major minor sort, I only get 5 product ID equal 1 values before I come into product ID 2, and then product ID 3 for quarter 1, et cetera, et cetera, et cetera. And then I'll see some more product ID 1s for Q2. But I basically have taken my table, I've said, I'm going to store this as a column store format. I'm going to sort it in quarter ID, product ID order. You know, if there's nothing that would limit me to 2 columns. I might sort on 3 columns. I might sort on 4 columns. I might sort on 1 column. But I'm going to sort in a major to minor way when I load this data into these columns. And then I'm going to store every column as a separate table. Now, the idea of compression is CPUs, remember, they're 1,000 times faster, and disk are only 65 times faster. So what we're going to do is we can use compression to squeeze those columns really, really small, and then make the CPU do the work of decompressing, because the CPUs are 1,000 times faster, and the disk are only 65 times faster. So we're going to trade I/O cycles by reducing the amount of I/O we have to transfer for CPU cycles to decompress that stuff that we read into memory. It turns out you can do much, because you have these values stored one after another in the column, in a column store. It's much easier to get really high compression factors than you can with a row store. Some people cite factors of 100. I think a fair number is you can always do about 3 to 10 times better compressing in a column store than a row store. I don't always believe the 100x factor that's sometimes cited. Now, if you've compressed this column store table and you've sorted it in one order, and you've taken some columns out of the table, you've stored those sort of together in some sort of sort order, you may have extra disk space to store the same columns or different sets of columns or overlapping sets of columns in different sort orders. We have to do something with those terabyte disks, and since we're not going to try to update these kind of databases, because they're mainly for read intensive, we'll store multiple copies, all as column stores, but perhaps sorted in different orders so we can run different queries very efficiently. Now, one of the very, very effective compression techniques is something called run length encoding. So with run length encoding, I take my sorted columns, which you'll see are quarter, product, D, and price, and I compress them, into tuples or rows that look like value, start, position, and count. So you see that quarter 1 starts at position 1 and goes for 300 positions. Quarter 2 starts at position 301, goes to 350, etc. I can do the same for product ID because it's sorted. Value 1 starts in position 1 and runs for 5 values. Value 2 starts in position 6, goes for 2 values, etc. Look farther down in there. So this is called run length compression. Price is not compressed. So now column 1, so that's a big takeaway. Column 1 might have had thousands of values in it. But in fact, after I've compressed it, it has exactly 4 rows in it. Now, they're not individual values. They're triples. The value, the start position of the value, and how far that run went. But I've compressed thousands of values into 4 little rows, triples, that represent the entire column. Another technique, and you've seen bit vector indices, is bit vector encoding. So here for every unique value, I create a bit vector representing that value. So here I have product ID. I'm going to create a bit vector for product ID 1, for product ID 2. And the bit is turned on if the product ID is equal to that value for that particular value in the columns, and then 3, etc. So that's a second technique, and that's pretty effective if the column only contains a few values. Turns out, once you've done bit vector encoding, then you can apply run length encoding to those bit vectors to squeeze out the zeros. So that's another compression technique that a lot of column stores employ. A third technique that I'm going to talk about is something called dictionary encoding. Here I take the column, I scan it, and I compute a dictionary. So I'm going to use the value 0 to represent quarter 1. So quarter 1 might have been a string, and not just Q1. But I can since there are only 4 values in the column, I only need 4 values in my dictionary. And then once I've computed the dictionary, I use it to encode the column. And now the column, instead of being Q1 or Q2, Q4, blah, 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 because it's perhaps not sorted, I couldn't use run length encoding, I've encoded it as values 0 through 3. But notice, if you know your binary arithmetic, I need just 2 bits to encode 4 different values. So you look there and say, oh, he's got an integer there, that's 32 bits. Nonsense. It's 2 bits long. So the first value in that column is 2 bits. The second value of 1 is 2 bits. The third value is 2 bits, 1 and 1, etc. So dictionary encoding frequently is used when the column is not sorted. And you can find a small dictionary, and then you can use the minimum number of bits to represent each value. Now you might say, wow, that's really hard. It's totally transparent to the user. Okay? The database system does this entirely under the covers. It will decompress as it brings the column values into memory. And again, we want to maximize the use of that. The data pipe is not very big. We want to maximize the benefit of what we transfer. Turns out, you take the same table and leave it as a row store and try to use run length compression. There are no runs to compress. You can use dictionary compression, but if you look at the stuff at the bottom right of your screen versus the top right, which is the compressed column store, you get almost no compression for this particular row store example. So turn out there's some very exotic techniques that can be applied to row stores that will do pretty well, but never any better than a column store. Now, once you've built a column store, it turns out you have to re-architect how the database system, and I want to talk about column store scanners versus row store scanners and some materialization strategies. I've skipped operating on compressed data. So if you look at this query, select names and age from customers where age is greater than 40, and you look at how a database system is architected, we start reading the rows off the disk. We read 8K pages at a time. We apply a predicate, and out comes the rows. Pretty simple. There's a disk I/O and there's a scan operator that's applying the predicate. Very simple to architect. Column store scanners, remember we stored these columns, name and age, in 2 different files. So we start reading the age file, the values in the age file, and we read those in really big chunks because we want to avoid seeks. Remember, sequential IOs are fast, random IOs are not fast. So we know we're going to read all these column values, so we read in big IOs. We apply the predicate. Well, that's not too hard, but what comes out is different. What comes out of the scan is not a set of values, but it's a set of positions and values. So this says the first customer, age 45, it's at position 1, it satisfies the predicate. Now we start a second, as that pipeline of data is flowing, we start a second scan operator where we use the position to filter the names. So Joe is going to come out. Sue is 37. She's not going to satisfy the first scan, the first predicate, age greater than 45. So Sue is not going to satisfy the predicate. So position 1 or position 2 will not appear in that position list that comes out of the first scan operator. So you already should see the takeaway from this is, wow, this looks more complicated. And I'll show you a little bit, another example in a second. So in row stores, there's this operator called the projection. In the target list of a SQL query, you list the columns you want. We use the projection operator to throw away columns. In column stores, we have the opposite problem. We have all these columns of the table stored separately, and we have to glue them together. And we call that materialization. And there are two strategies you can use when building a column store. The crummy way to do it is to do early materialization. Doesn't have as good a performance. And the right way to do it is late materialization. And I'll give you an example. So here's my table. I have product ID, I have store ID, I have customer ID, I have price. Now, notice the only thing I have compressed in this example is product ID on the left. So product ID 4 value starts in position 1. There are 4 values of it. And just to simplify the example, I didn't compress anything else. So with early materialization, I do the following. I take the 4 columns involved in the query from the table, and I decompress the product ID, and I immediately spit out a bunch of rows, and then I can feed them into my normal relationship.